Sorry, just told me when I woke up tomorrow and looked at my phone
I was going through everything.
No
Everyone
notifications.
said anything.
No.
The mission was great. Like the roads were great. Everything was fine.
All right. Today we're going to talk about area under the curve. And we are going to approximate area under the curve using some rectangles. Okay. So just kind of like hang tight with me for a moment. Okay. Sometimes we can use geometry to find area. Well, not sometimes, like all the time. Okay. However, not always do our curves, especially if we think of like polynomials. Polynomials don't really take the shape of something that we're used to finding the area of in geometry, right? We can find the area very quickly for circles and triangles and rectangles and trapezoids, but, curves, there's really not a good process for that, okay? So what we're going to do today is we're going to find the area under a curve, but we're going to approximate it with a shape that's easy for us to find, a rectangle, okay? So you really don't have to write this down. I want to show you something. The three things we're going to do today . Okay. The three things we're going to do today is we're going to look at finding area under the curve using rectangles when we use what's called left endpoints, right endpoints, and midpoints. Okay. So we're going to take a chunk, we're going to section it up, and we're going to create rectangles. Here we go. All right. So here under this curve, you can see I use the very right end to make rectangles with, okay? Here, I'm using the left side of my rectangles to touch the curve. And here, the midpoint of each rectangle is touching the curve, okay? I'll show you how to get all that, all right? But I want to show you this real quick. Oh. Cross your fingers that this is there. All right. So here I have a picture of a curve, and I have left endpoint rectangles. Now watch what happens when I increase the number of rectangles. When I increase the number of rectangles, what's happening to our area? It's going to be more accurate versus the less rectangles I have, the more, it's not quite as accurate. We still have a pretty good estimate, but it's not as accurate. The more rectangles we get, the better. Notice, and we'll talk about this, how some rectangles sit underneath the curve, some sit outside of the curve, okay? So here's right, that was left. Here are right endpoints, okay? And then here are midpoints. Okay. Once again, the more we have, the better we are. Now, that is tedious. This, not so bad. Okay, we can find those rectangles and approximate the area. All right, so this is what our strategy is going to be. All right. Sorry, I don't want this to be overwhelming. All right, we are going to decide how many rectangles we need. So you're going to see the word subdivisions. Divide up your chunk of curve into so many rectangles. Oftentimes you're going to be told what that is. Okay, I'll say this many rectangles, or n is 4. Okay. You may want to even write down that is n. The number of rectangles is represented with n. Then we are going to figure out if we're using left, right, or mid points. Now, this will either be given to you directly, or you're going to have to deduce it with some information. Okay. We are then going to have to figure out how wide our rectangles are. Okay. We're going to have to figure out how wide our rectangles are. And in order to do that, we need to figure out how often x changes. Okay. You're going to be given an interval. All right, so you need to take the interval and figure out how wide the interval is and split that up amongst your rectangles. So you're going to take your end points and subtract them so you know how wide your interval is, and then divide it by n, the number of rectangles. In order to find area, you need to know how wide your rectangles are. You need to know how tall your rectangles are. So you're going to have to figure out the heights. Since we're using a curve, your function value gives you how tall the curve is. So as long as you know the y value at each of those x coordinates, you know how tall your rectangles are. And then you get to add base times height, plus base times height, plus base times height, plus base times height. And that's it. Now, depending on if we have left, right, versus middle, to make our rectangle's width, that's going to affect each of these heights. Okay? So, I'm going to hand out, call this a foldable. Okay, you have scissors in front of you. Please don't do anything with this until I instruct you. Okay, I don't want you to cut or fold somewhere you're not supposed to. Okay, I want to organize all in one place the different ways we can do one problem. Okay, so you're going to need this today and tomorrow. So take this, the way I hand it out to you, and do you see how there's like lines? You need to fold along this line so that it's the inside. The lines go on the inside. But you need to fold along that line. I'll turn the light on for you so that those lines are on the inside. If you want to fold it the wrong way and then fold it back, that is up to you. Okay, now open it up, and what I want you to do is take your scissors, everybody eyes on me, You're going to cut these 3 lines only until the fold. So it's like you have 2 little, or you have like 4 little book flaps. Okay?
The way that you said eyes on me is put me back. Like the
Yeah,
frame.
while I'm holding little scissors.
While you're holding scissors, yep.
Tiny scissors.
Well, I have found that if people will just try to do it by themselves without listening to me, they cut too far and they're frustrated that they didn't listen.
Basically, people are
That is not the word that came out of my mouth whatsoever. Nor did I infer that.
exciting.
All right. So now, put the scissors back in the middle. If they're going to be a distraction to you, maybe you should put them on. Okay. All right. So we're going to go through 3 of these today. The 4th one's going to be tomorrow. All right. So go ahead and open up the first flap, and it says, it talks about the left-hand sums. Okay. In a left-hand sum, the height of the rectangle is given by the function value on the left side of the interval. All right. So let's go through. I want to find the area under this curve, and that's the picture on the front, from 0 to 2. So I'm going to tell you that we're going to have n equals 4. Let's figure out how wide our rectangles need to be. Okay. So delta x, and I would do this like on the inside here. Okay. Delta x is b minus a, so I'm going to take our interval b minus a and divide it by the number of rectangles we want. So if we want 4 rectangles, we're going to divide by 4. Okay. So what's our change in x? That's okay. So, go back to your picture. We need to draw rectangles that are a half of a unit in width, which means from 0 to 1, 0 to 1/2, I'm gonna have a rectangle. From 1/2 to 1, etc., etc. Now, if we are using the left side of the interval, or the subinterval, to make our rectangles, then this would have no height, because the left side is at 0. All right? Now, from 1/2 to 1, we would come up and put the left side of the rectangle on the curve. From 1 to 1.5, we're going to make the rectangle where the left endpoint hits the curve. And then from 1.5 to 2, we draw our rectangle so that our left endpoint So we need to find base times height of this, plus base times height of this, plus base times height of this, plus base times height of this. So open up your little flap, okay? And I will do the work in this empty space over here. All right. My picture's up here for you to reference, okay? So our area, we need to sum up 4 rectangles, okay? This rectangle has width of 1/2, and its height is wherever that coordinate is right there. So it's f of 0. I know that we know it's 0, but I'm really taking baby steps here. Okay. Our next rectangle, this one, has a width of 1/2 and its height is whatever that coordinate is right there. That's what's touching. All right, so we would find that that's the y value at 1/2. Our next rectangle has width of 1/2. And its height is coming from this y value right here, f of 1. And then this rectangle has width of 1/2, and its height comes from whatever this coordinate right here is. So the y value at f of 3/2. Okay, now I'm going to do this, but I need you to be able to see what's happening. Okay, what's true about every single width? It's the same. So width is 1/2, and we can just multiply by the sum of the heights. We can just like factor that out, right? Okay. Well, how do we get the heights? Okay. Well, how far apart are each of our rectangles? They're all 1/2 apart because that was delta x. Okay. We start at the very left at 0, and then our next is 1/2, and then our next is 1, etc., etc. So our function is y equals x squared. So when I plug 0 into y squared, our y value is 0. When I plug 1/2 into x squared, our y value is 1/4. When I plug 1 into x squared, our y value is 1. And when we plug 3/2 in, we get 9/4. We have 14/4 times 1/2. So we have 7/4. What? Unit squared? Yes, we are talking about square units. All right. Should we go to our right hand rectangles? What did you say? And what did you say? Alex thinks it might be the same. Let's look at it. Okay. So open up the right hand. Okay, so it's going to be the third one down. Okay, the right hand is going to be the third one down. Note that n is going to equal 4, and our delta x is still b minus a over 2. Okay. I don't know if you want to write that down again, but in case you do, go ahead. Okay, Alex, our left-hand endpoints that we just calculated, was that over or under what the real area would be? That was under because we had some spaces, right, underneath. All right, well, let's look at this one. So from 0 to 2, our delta x, once again, is 1/2. We're doing the same thing. But now, when we make a rectangle, we want to draw it so the right side hits the curve. Alex, is this going to be the same? No. Okay. So do you see how we're drawing the right side of our rectangle to hit these 4 spots? So now our area is going to be more than the real answer. Okay. All right, look at, I would open your flap so we can do the area. So for our area, we're going to have 1/2, because that's how wide this rectangle is. You know what, I'm going to start at the right side. Since we're doing right-hand endpoints, let's start at the right side and work our way left, okay? Because on the right side, our height comes from this coordinate, f of 2. Here, this rectangle has a width of 1/2, but then its height comes from this y value at 3/2. Our next rectangle, our height is going to come from the y value at 1. And then our next rectangle, our height's coming from the y value at 1/2. Okay, so notice how these are all of the y values, but this time we're starting on the right side and going down by 1/2. Okay. I don't think that you ever want to really set it up like that. If your rectangles all have the same width, I am fine with you writing 1/2 times and writing the sum of your bases, or the sum of your heights. Okay. So the height at 2 is going to be 2 squared. The height at 3/2, we're just plugging into our original equation, x squared, x squared, x squared. So just to save you some time, this comes out to 15/4. It's not surprising that this is more, because we can see that our rectangles are over the curve. Okay, we know that this is an over approximation. We know that from our picture, this is an under approximation because all of these rectangles sat underneath of our curve. Questions so far? Really, we're like back to geometry, right? All right, let's talk about our last one. Let's talk about the midpoint. So that's the middle of the 3 flaps that we're working with today on that handout. So n is still going to be 4. Delta x is still that 2 minus 0 over 4 for our 1/2. Okay, we're doing the same problem 3 times. Okay. Well, now when we go to our picture, when we draw our rectangles, we want the midpoint to be what gives us our height. So in this case, we go to the middle of our interval, and that's the y value that we want. So a little bit of our rectangle is hanging over, and a little bit of our rectangle is under the curve. So maybe for this one, can we all agree that the width of each rectangle is 1/2? Okay. So are you okay if I just say our area is 1/2 times, and we can figure out what all the heights are. Like, can we just go straight there? Is that okay? Okay. Now the midpoint gets a little tricky because we have to figure out what the midpoint is everywhere. Okay? So what is in between? So this first rectangle goes from 0 to 1/2. What's the middle of that? Okay, so we want the y value at 1/4 for the height. Okay? What's the middle of 1/2 to 1? Okay, so we want the y value at 3/4. And then this rectangle, okay, we can keep playing this game, or we can remember how far apart are each of our rectangles? 1/2. So each of our midpoints are going to be 1/2 apart. All right, so 1/2 later would be 5/4, and 1/2 later would be 7/4. And we can just do that instead of like find the middle of every single rectangle. So our area is 1/2 times f of 1/4. Okay, we're going to plug that into our function. We're going to plug 3/4 into our function. We're going to plug 5/4 into our function. And we're going to plug 7/4 into our function. Our function is x squared, so these are nice and simple numbers. Okay. So we're going to get, I'll just let you know, 21/8. And it shouldn't be surprising that that number is in between the left and the right approximation. Okay. One approximation we knew was way over, not way over. One was over, one was under. This one's closer. Okay. If I made you do this with 6 rectangles, what would be true about our area? It would be more accurate. All right, I want to talk about 2 vocabulary words, and then we'll do an example that's not on this pink sheet. So if you need to transfer back to your notebook for a moment. Okay. I will either tell you left, right, or middle, or I might say, give me an over approximation, give me an under approximation. Okay. So if we're going to have an under approximation, our rectangles need to fit under the curve, and we call those inscribed rectangles. They're fitting under our curve. If we want an over approximation, we want our rectangles to like overflow from our curve, and those are called circumscribed rectangles. Those rectangles are like overflowing from where the curve area would really be. So we're going to do one example. And maybe you'll be back before we do that. I don't know. We're trying to do as much as we can. Have like some calculus kids talk to the pre-calc kids about what it's really like to be in calculus and pre-calculus. Okay? They both have different perspectives, and Max is also in stats. Here is our example, and we're gonna just do one of the 2, but I would love to do upper and lower. We're gonna pick one. What do you guys think? Upper or lower? Lower. Okay, we're going to find the lower sum from 1 to 2 when n equals 5 of y equals 6 minus x squared. Okay. Well, n is 5. They give that to us. Go ahead and calculate for me delta x. Once you get things written down that you need, calculate what delta x would be. Brayden, how do we calculate delta x?
B minus A over N.
All right, so how do we do that here?
B minus 1 over 5.
Okay, so delta x is 1/5. Now, if this is a lower sum, do we want right-hand endpoints or left-hand endpoints for our picture? Okay, if we draw right-hand endpoints, because we're decreasing, we would get an under approximation. Okay. Now you don't technically need the picture to do this. What we know is that our area is, well, we have 5 rectangles. And how wide are they? 1/5. So we know we have 1/5 times the height, plus 1/5 times the height, plus 1/5 times the height, plus 1/5. And I'm going to start, since this is a right-hand approximation, let's start on the right-hand side and work our way left. And this time I'm actually going to do it so my work does that too, so we keep things in order. I didn't do that last time, and I'm sorry about that. But since we're on the very right side, this very right rectangle has height of f of 2. Okay. Our next height would come from which x value? Okay. Our delta x is 1/5. So 9/5. And then our next rectangle has a height of f of 8/5, and then we'll jump over to 7/5, and then we'll jump over to 6/5. And we have 5 rectangles. I have my 5 heights, so we're good. Now it's a matter of you plugging and chugging. 6 minus 6/5 squared, what's that number? And add it to 6 minus 7/5 squared, and what's that number? And add it to 6 minus 8/5 squared, and what's that number? Okay, it's a lot of you punching numbers into the calculator in order to get your answer. Okay, once you set up, it's plugging and chugging. Quite literally. So my main concern, do you have a question on how we set it up? Do you have a question on how we get these numbers right here? Yes.
Not on those numbers, but I was just wondering, so they're supposed to give you the N? Because they didn't give it to us on like the packet thing. But like,
Right. So I told you that, and so either I will tell you or the book will tell you. You will always know. Yeah. How'd it go?
Well,
Okay.
there weren't many questions.
Yeah, well, and I'm not gonna lie, most of that class was serious. He had a good point, so.
They were like half senior.
Well, like half senior, in the sophomore.
All right. So in your assignment, a lot of it's going to be left and right. Please look at my gold sheet because I specify on 2 problems that I want you to do the midpoint approximation. So you are doing on your gold sheet the second assignment from 4.2. The second assignment from 4.2. So it looks like it's page 263, 25, 27, 29.
Oh,
Goes on. Okay? You see what I'm talking about there?
You lost your bullshit I lost my
Oh, and I'll be
in
gone
stats. That is our year long.
Are we still having the quiz on Monday?
It's a cheat
On
sheet.
Monday,
Because
yes,
you're
I'll get you.
and you're allowed to use it on tests.
Oh my god.
I lost.
This is our worksheet for tomorrow.
Okay.
Organizational skills.
Okay. If you're a junior, hold on.